Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering is neural networks. And this is the fourth topic in the list of topics which are covered in this course. And this topic of neural networks is divided into two subtopics, Lecture 4A and Lecture 4B, which is this one, which is of slightly higher complexity as compared to Lecture 4A. So these are the list of topics which are covered in this course. And we are at the fourth topic, which is neural networks, which consist of 10 questions and answers. Basically, these are concepts. So this is the list of concepts which will be covered in the lecture 4B, which are highlighted in green color. So without further ado, we move on to the details of these concepts. So we are at the topic 4B. What are the question and answer, or the question is, what are the limitations and challenges of neural networks? So this is a very interesting question, and there are certain examples here which show the issues and the challenges of neural networks. So we have been discussing, and this course is about the power and the powerful capabilities of neural networks, but they have their own range of limitations and challenges, right? And of course, with those limitations and challenges, their implementation and their practical deployment can get hindered also. So here's a list of some of those challenges: data dependence, computational cost, which is kind of understandable, right? Because you need to have enough data, or the model may fail to generalize, or it may fail to learn. Okay. And then, of course, is the computational cost, and with the computational cost comes the energy cost also. So this can be very resource intensive, okay, requiring GPUs or TPUs and so on. So we will touch upon them, and we will also touch upon what this figure is showing. Is very interesting. So let's start with the data dependency. So we have seen that when we do back propagation, and we'll see further towards the end of this lecture, there has to be large and labeled data sets to learn effectively. And if there is insufficient data, or if there is the quality of the data is not right, this is what we're talking about. If the quality of the data is not right, okay, then of course this that neural network may fail to generalize, and this may result into poor performance. Now try to understand that this dependency on the data, okay, limits its usefulness, obviously, and to those domains where the data is scarce, or the data is there but the data is expensive, or the data is there but the data is hard to obtain. So that's the issue of data. So we have that wonderful neural net and everything, but still when the data is not there, it's data driven. All right, then is the computational cost. So the computational cost, uh, training, because the training, looking at the back propagation, requires significant computational resources, okay, and that repeated forward and backward passes across many layers, especially for especially for large data sets, okay, that can lead to long training cycles and high energy consumption, okay. So as a consequence, it will become, or it is impractical for those environments which are resource constrained, or which require real time responses, because it takes time and resources. Okay. So then is the black box approach. So what is the black box approach, or the black box concept? Is that we know that there is mathematical foundation behind neural nets. We will discuss a chain rule also, and we know all those things. But still, back propagation contributes the black box nature of neural networks. Now, it is adjusting the weights without providing the interpretability. It is just like comparing, okay, compare, this is not the one, this is the actual, this is not. So there is no interpretation. So it is very difficult to understand how the network arrives at a specific decision, especially uh, those fields which are critical, which are well regulated, where safety is very important, such as healthcare or finance. So this is the example here. This example, I'm sorry about that. So let's look at this example. So we know this is the face. This is a person's face. This picture has all the so to say the ingredients of a person's face, but this is not a person's face. So this is the black box approach of neural net. So when this goes in, so we say, okay, uh, it is a face. Why it's a face? Because because it has certain things, right? And those, it's not an apple, okay? And how to verify it automatically, how to trust the network, that we really don't know. Because when this picture goes in, okay, then of course it says it's a face. This is the true. This is true. This is not true. So how to find out this is a failure point, and how and where the failure occurred, and how to improve it? You don't know. That's why it's the black box approach. Understand? That's why it is a black box. That's the problem. Okay, now overfitting risk. So back propagation can lead to overfitting, especially when the model is too complex. Uh, Too complex for the available data. So it's kind of a data issue also. So what it will do, it will memorize patterns instead of generalizing them. So what's going to happen, that the performance will be excellent on training data, but it will be poor, okay, for unseen or real data. So let me show you. Let me close this. Just hold on for a sec, please. Okay. So this is the case over here. So we have this unlabeled data set, okay, and then we perform a decision, so to say, and this is underfitting. Why it's underfitting? Because it's linear. It's underfitting. It's linear. So this relationship is not captured. This is a balanced approach. Okay, so we see that over we have kind of a uh, discriminating function which is like quadratic, and it successfully divides the two classes, and this is overfitting. So in overfitting, in real this is very precise. This is very precise, and in real life we may not get data, okay, and basically this is due to the problem of having insufficient data also, or basically of this being very complex. So this is overfitting, and of course that is going to result in inaccuracies for unseen data. All right. So next is next is this one. So adversarial vulnerability. So what is that? Because these neural networks, which have been trained using back propagation, they are susceptible to adversarial attacks. So what are those adversarial attacks? That there is an introduction of very well crafted and small inputs, okay, that mislead the model. Why it happens? Because of the vulnerability in the sensitivity of the model to certain inputs. And these are aware of the attacker is aware of them, and the attacker exploits them, okay, to produce confident but incorrect predictions. And of course, that raises concerns about the robustness and security. So this is a cat, we know that. And then a certain adversarial perturba- perturbation is added to it. It is very small, and the model, of course, recognizes this picture or categorizes the picture as that of a dog. And of course, that has some real implications, and there are many serious issues with this. And of course, if you want to, I would suggest that you read all of this. Now, remember one thing, that these references, this is in addition to the textbook. This is not the stuff from the textbook. Okay, because of the diversity of the nature of this course. Okay, I don't believe a single. This is a wonderful book, the first one, but because of the diversity of this nature of this subject, it cannot be limited to a single or couple of textbooks. So there's a lot of material to read, and of course, there are many interesting diagrams also, which are referred here. So I would suggest that you don't limit yourself to the book alone, because the book has its own the way it is has been developed. So what would you estimate? So we see that it appears that with the neural nets or deep learning, the machine is intelligent. So we are aware of, maybe if not now, you should get aware of, there's something called as the IQ, or the intelligence quotient. So the question is that how would you estimate the intelligence quotient of the best neural network? Okay, so for this we look at this example here. So basically, intelligence quotient is the ratio between the mental age and the physical age of a person. Okay, so now we cannot like apply the age to a machine or to a neural net. So there is certain research which will just shown in this diagram. So the intelligence of a neural net is task specific. For example, neural networks that excel in specific tasks like image recognition or language translation. Okay, they show so to say high IQ. Now this IQ is in double quotes. This is not the literal meaning. And performance within that high performance within narrow domains. However, their intelligence is again in double quotes, is limited to these predefined problems. Okay, and so that is not the way humans work. If a person is intelligent, that person is not intelligent only in recognizing images. That person is intelligent in other parts, or the way that person lives, or presents him or herself. But in the case of machine, okay, that intelligence cannot easily be transferred, or the knowledge cannot be transferred across unrelated tasks. So that is, so this type of intelligence is different from the type of intelligence we are used to. Then is the general intelligence. Unlike human IQ, okay, IQ is again in double quotes. Neural networks, they lack general intelligence. Okay, they basically struggle with abstract reasoning. There is hardly any reasoning. It is just kind of hallucination. Okay, and they lack common sense. Common sense is very uncommon in intelligent beings like humans. They lack adaptability. Okay, the machines. So it is very challenging to estimate a single IQ, the general intelligence, and that general intelligence reflects uh, broad intelligence or abilities beyond specific tasks. So if a person is intelligent as I said before, then that person is intelligent in other parts of his or life also. That intelligence is reflected. So that is general intelligence. That is not the case for machines. Okay. Then are the benchmark comparisons. All right. So when we estimate the IQ, okay, we use benchmark tests, right? And for neural networks, okay, how can we compare against those tests or other AI models? Because the reason being that these benchmarks, what they do is they evaluate task accuracy, the speed, and the complexity, and the list goes on, okay, but still may not fully capture the depth of intelligence, right? And then then we say, okay, now let's do some hypothetical comparisons. Hypothetical comparisons like pattern recognition, general problem solving. Now we know that neural networks typically outperform humans in pattern recognition, but lag in versatile problem. For example, they lag in coming up with stuff. Original stuff, even with large language models, there is a limited number of jokes, and those jokes are basically presented in different ways because a big sign of an intelligent person is that person has a sense of humor, can crack jokes. So machines, they don't crack those jokes. So there is research, repetition of the jokes. So that highlights the gaps between the capabilities of AI and the human intelligence. So what are those? For example, pattern recognition, like neural networks, like they like superhuman skills and speed. But when we so when but when we look at general problem solving, okay, then they lack uh, uh, they lack they don't have the kind of a response as humans have. I gave you the example of jokes. They lack flexible reasoning. They lack creativity and those things which characterize humans. So this example here, let me discuss this example with you. So this was a specific example which suits the machine. So you can read it. So basically, we have these. So what's going to be the next pattern? Okay, what if we have this sequence? What would be the next pattern? Now, this specific example you can use. One could use certain types of operators. Okay, so those when you apply those operators, only then you can have a certain. This is a typical kind of an IQ question. Okay, so the point over here which I'm trying to make is that this is a question, IQ question for a limited domain. Okay. Now this is for a specific type of data set, procedurally generated matrices data set. Okay. So we have these eight pictures and we have to identify which should be the next picture from these. Okay. And of course there are certain several candidates are plausible, right? So this kind of and kind of pattern matching machine can do, but that is a very limited domain of the IQ test. Okay, so of course this is not from the textbook. Okay, and of course if you want to know more about it, so you can read it, right? So what is back propagation and why it is used in neural networks? Now we have been referring to and mentioning basically this is the short for backward propagation, which is not the logical inverse of forward propagation. Remember that, because there are a number of things which happen in backward propagation. And why is it used in neural networks? So this backward or back propagation is used for error calculation. Error is the difference between the true label and the predicted label, and it involves a gradient computation also. And then based upon this, the weights of the edges are updated. and that of course happens at the level of layers, right? The biasness which we mentioned before at a layer level, and then of course efficiency optimization. So let us go through them, those things. Okay, backward propagation or back propagation is part of the training of the neural networks, right? So how it helps, that it helps the learning, the process of learning. This is uh, this whole is backward or back propagation. So it is used in training the neural network, right? And it helps the learning by how? By adjusting the weights. These weights are adjusted, okay? By adjusting the weights, right? And how are those weights are adjusted? Based on the error between the predicted and the actual output, right? So this is the error difference between the predicted and the actual output. And this backward or back propagation, okay, this is part of what is called as supervised learning. And of course this is used in conjunction with, together with the gradient descent. And here it is, gradient descent. So what are the steps? Let's look at those steps or the bullets. So first is the error calculation. So how is that error calculated? Uh, how far or difference between the prediction made by the neural network from the actual function using a loss function. Okay, this is the step one here, right? And without calculating this error, how can the network determine how well it is performing? So this is necessary. So this error basically is sent backward to the each neuron, okay, and then the weights are adjusted, and the weights are adjusted. Then is the gradient computation. So what happens is this gradient computation. This gradient, as a matter of fact, tells us that how much that weight contributes to the error. And this back propagation uses the chain rule, which we will cover, discuss it. And this is done. This is done layer by layer. So this is the mathematics behind is the chain rule, and this back propagation and gradient descent is essential and critical for updating the weights, actually effective updates of the weight. So what it does, it helps and it allows the neural net to minimize the loss function during what? During the training, and increase the predictive accuracy, right? Then is the weight update. After those gradients are computed, the network updates its weights to reduce the error. Okay, over here. And this is used, which we have seen using the gradient descent. And of course, the model learns through the data. Okay, and as this moves through this iteration, back propagation, forward propagation, backward propagation. So what happens is that iteratively this error reduces. Okay, until it reaches a point which is called as the diminishing returns. So at this point, and basically further it takes more effort to uh, as a matter of fact get any positive gain, right? So that's all. There can be other criteria also. Then is the layer wise learning. Now this is done layer by layer. Okay, so by distributing this error backward, okay, through the network. So why? Because this will ensure that all the layers, not just the output layer, contribute to the learning. Okay, the learning is the learning is reflected right? And of course, the parameters for each layer are adjusted accordingly based upon uh, the the final prediction, which is specific to that layer, which is specific to that layer. So you cannot have the same weight adjustment for all the layers. It would be like a naive approach of using the same medication to cure or to attend to all the diseases or the ailments. And then notice efficiency optimization. This back propagation, as a matter of fact, streamlines the training of deep neural networks. Okay. How and why? Because it kind of systematically reuses the computations and applies the chain rule. Okay. So what happens? This makes it computationally feasible for training of large data sets, for large models. Understand? And of course, this also, because of this mathematics and the concept behind it, it integrates well with the hardware acceleration and deep learning frameworks. Okay. Resulting in scalable and fast training. Okay. So I'm sure that you are not going to find this diagram in the textbook, because for your benefit, a lot of search has been done over the internet, and a lot of material has been used for your benefit, and this is the list of those references. Okay. All right. So I mentioned a chain rule. So how does back propagation use the chain rule of calculus? Okay, this is very interesting. So this diagram, this basically here is the chain rule. This is the chain rule, okay, which you must have studied in your college, okay, in a calculus course. And this is how the chain rule is used. This is how, so this is basically the forward pass and the backward pass. And this is how the chain rule is used, okay, for the neural network. So that's the mathematics behind it. I will discuss it. So this back propagation, it relies heavily on the chain rule. Okay, how it relies, because for gradient calculation across layers. So we have discussed this, and we have seen that when we are training a neural network, what we are doing, that we are trying to minimize the loss function. Okay, and by adjusting the weights and the biases. So the loss function, of course, depends on many nested functions. Okay, and each layer in the network, okay, uh, represents a function of the previous layers. The output of a certain layer is the input of the next layer, and the output of that next layer is the input of another layer. So this is layer by layer. So when we update each parameter, okay, we need to calculate how the loss changes across the layers with respect to that parameter. Now, since each parameter's effect passes through many intermediate layers, so it has kind of a ripple effect. So what we do is that we apply the chain rule, okay, to systematically compute these gradients across all the layers, okay, so to take that ripple. So how do we go about it? So we have a layered computation. So this back propagation applies the chain rule across the network's layers. Okay, let me zoom here. It applies the chain rule. Okay, so we have, if f and g are both differentiable, this is f and this is g. If they're both differentiable, okay, and fx, this is fx, okay, this is f dash x. So if fx is the composite function defined by, okay, Then f is differentiable, and how it is, you can read this basically. So this is how it works. Okay, so we have f g of x, right? And this is how it becomes differentiable. So in plain English, what the chain rule tells us, that the derivative of the outer function, okay, if you take the derivative of the outer function, all right, the outer function, right, and multiplied by the derivative of the inner function, multiply with the outer and the inner function, okay, uh that's it. So for example, the derivative of uh sine 5x is cosine 5x into 5. That's it. So this basically, the chain rule was discovered in calculus by Isaac Newton and Leibniz in the 17th century. So that's the historical part. So we can see that the derivative with reference to x, this is chain rule, right? And the derivative with reference to y, this is the chain rule, okay? And then of course this red is the backward propagation, and the black is the forward propagation, okay? And we are using it for the reflecting the change across the layers, right? So that's what we are doing. So let me zoom out. Okay, so to reflect the change across all the layers, chain rule is used. So that's the mathematics behind it. All right. Gradient decomposition, what is meant by gradient decomposition? Basically, what the chain rule does, it breaks the gradient into smaller manageable parts. Okay. And then by virtue of back propagation, this is used uh, in decomposing, in breaking down the total loss, okay, into partial derivatives for each layer. Now what it does is that this modularity makes it feasible to compute the gradient, okay, even with deep networks with many layers and parameters. So that's the benefit and the beauty of the chain rule, okay. So this is the partial derivatives I was referring to. Okay, then we something called as recursive derivatives. So these derivatives are recursively calculated, okay, by reusing the results from the latter layers. Now, when this recursive structure, as a matter of fact, kind of mirrors the chain rules, okay. And what are the those requirements to multiply the derivatives step by step? So at the end, what we get is gradients, okay, which efficiently and accurately, okay, uh, for each weight and the bias in the network. So that's the benefit. Efficient reuse during this back propagation, which we discussed before and discussing right now. So there are intermediate values like activations and partial derivatives. They are cached, okay. Why? To be reused, so that kind of reduces the calculation and the energy consumption and the redundant computations. Now this efficiency, how it is made possible? Because of the chain rule. Why? Because many derivative terms which appear repeatedly, okay, and then they can be kind of recycled. This is more or less like dynamic programming. So, and of course, dynamic programming is a topic which will be covered in this course. And finally is the error attribution. So, using this chain rule, okay, uh, and then using the back propagation. So the error gets attributed to specific neurons and specific connection. Number one. So what happens is that each layer's gradient reflects, okay, each layer's gradient reflects its contribution to the overall loss, because there is a single output and all the layers contribute towards that output. So the loss should be attributed accordingly. So this is the mathematical clarity or the modeling that helps the network to learn what which weights need more or less adjustment. So then we move on. So all right. So if you are, as I said, I have been repeating, you are again not going to find this in the textbook. So, and of course, this is what the chain rule is, right? And if you are interested, everything is referenced here, including that figure also for your benefit. So everything is referenced if you would like to read more about it. So now we come to the end of this so to say, this the topic or the subtopic, also subtopic in the context that this is 4b, topic that this is neural nets. So what are the common challenges or limitations of back propagation? So this local minima and overfitting, and this we have already discussed, we know that. And overfitting risk that we already discussed, computational cost is obvious. So we will spend some time on the vanishing gradients and the exploding gradients. Vanishing gradients we also discussed in the context of plateaus or saddle regions also, not in a lot of detail. Okay. So with reference to the vanishing gradients, basically when what's going to happen? So what's going to happen is that it is successful, right? But this has some issues, right? So when the gradient becomes increasingly small, okay, and they are propagated back through many layers, okay, especially with the activation function being sigmoid or tangent, okay, this can stall learning, especially in the earlier layers of the network. And then for the exploding gradient, when the gradient grows exponentially, that kind of destabilizes the training and cause what is called as the numerical overflow. Of course, both issues are problematic, and these are more problematic in recurrent and very deep networks, which we will discuss. We have recurrent neural nets as a topic, so you need special architectures. So, what are vanishing gradients? Okay, so this is the example of a vanishing gradient, right? So this vanishing gradient basically uh, they are basically when I've already discussed this basically. So this is basically, so now we are towards the end of this subtopic. I call it subtopic because it's 4b. The topic is neural nets. So what are the common challenges or limitations of back propagation? So let's look at them. So basically, we know that back propagation is a core learning algorithm, and this allows to update the weights, right? And it has been very successful. And but still, it has several significant and major challenges and limitations, which basically affect the performance, which affect the stability, which affect the efficiency, especially in deep networks, because because as I mentioned, that ripple effect through the chain rule, okay, that is more profound for deep networks as compared to shallow networks. So what is vanishing gradients? What is vanishing gradients? As this is shown in this picture also. So we have the output, and as we move towards the input, right, the gradient, as a matter of fact, decreases, it falls down. So for deep networks, this is as shown in this picture. With back propagation, gradient can become extremely small. Okay, especially for certain activation functions like sigmoid. So what happens? What is the consequence when this gradient is very small? These earlier layers, this layer one, layer two, and layer three, okay, their learning becomes very slow, or they do not learn at all. Why? Because the gradient has fallen, has reduced. So what happens is that the network either fails, or it is hard for that network to capture long range dependencies, okay, or deep patterns effectively, right? So for example, if we have a certain picture with a with higher level of hierarchy, okay, so in that case this vanishing gradient is going to affect it significantly as compared to simple pictures which have which have shallow hierarchy, so to say, right? So that's one point. The other thing is the exploding gradients. So what are exploding gradients? As you can see in this picture here, exploding gradients. All right. So the gradient grows excessively, large in very deep or poorly initialized networks. So what happens that it leads to unstable weight updates, okay, or it causes the model to diverge and produce not a number values NaN. And of course, like the vanishing gradient, it can severely disrupt training. And you have to control this using something called as gradient clipping, or you have to use properly initialize. And then is the local minima that we have discussed thoroughly before. Black propagation may get stuck in local minima or saddle points in the loss surface. Loss surface we have discussed, and get stuck where the error is not where the error isn't globally optimal. So there are techniques which kind of escape the shallow minima, but the risk is there, especially for the networks which are not properly tuned. And then is the risk of overfitting that we discussed number of times. So if the network is too complex or the data set is too small, then overfitting can occur. So when overfitting takes place, then of course generalization is at a loss, and there is a high accuracy for the training, but poor accuracy for real world performance. And last but not the least is the computational cost and the cost of GPUs or TPUs and energy and requirement of specialized hardware, and the list goes on. So these are some of the issues and limitations, and of course they need to be looked at and resolved. So this is all for this. Thank you very much.